So today our topic is Bayesian decision theory. In classification, Bayes' rule is used to calculate the probabilities of the classes. So in today's slide, we will discuss how we can make rational decisions among multiple actions to minimize expected risk. Moving towards our next slide of probability and inference, tossing a coin is a random process because we cannot expect or predict at any toss whether the outcome will be a head or a tail. That is why when we toss coins or buy lottery tickets or get insurance, we generally predict. We can only talk about the probability that the outcome of the next toss will be a head or a tail. We define a random variable that takes one of two values, let's say x, where x equals to 1 denotes that the outcome of a toss is head, and where x equals to 0 talks about the outcome of the toss is a tail. Such x are Bernoulli distributed, where is the probability that the outcome is head is p of x equals to 1 equals to p0 to the power x of 1 minus p0 to the power 1 minus x. The sample is x equals to x to the power t, the limit of t and n where t equals to 1, and the estimation is p0 equals to number of heads by number of tosses is given by this formula, and the prediction of next toss is heads if p0 is greater than half and tail otherwise, where p0 is the parameter that uniquely specifies the distribution. Let us say, for example, we observe customers' yearly income and savings, which we represent by two random variables, x1 and x2. Some customers in the bank are low risk in that they paid back their loans and the bank profited from them, and other customers are high risk in that they are defaulted. Now the prediction we can choose is c equals to 1 if p of c equals to 1 by x1 comma x2 is greater than 0.5, that is half, or else c equals to 0. Or choose c equals to 1 if p of c equals to 1 by x1 comma x2 is greater than equals to p of c0 by x1 comma x2. Otherwise, c equals to 0. Bayes' rule. It is called a prior probability because it is the knowledge we have as to the value of c before looking at the observables x, satisfying p c equals to 0 plus p of c equals to 1 equals to 1. Now, p of x by c is called a class likelihood and is the conditional probability that an event belonging to class C has the associated observation value x. P of x is the evidence. This is the marginal probability that an observation x is evident, seen regardless of whether it is positive or negative. Example, p of x equals to p of x by c equals to 1, p of c equals to 1 plus p of x by c equals to 0 multiplied p of c equals to 0. Combining the prior and what the data tells us using Bayes' rule, we calculate the posterior probability of the concept p of c by x after having seen the observation x. So this is the Bayes' rule where posterior equals to prior multiplied likelihood by the evidence. The prior is P of C. Because of normalization by the evidence, the posterior sums up to 1, where P of C equals to 0 by x plus P of C equals to 1 by x equals to 1. Continuing with Bayes' rule. In general case, we have K mutually exclusive and exhaustive classes Ci, where I belongs to 1 to K. The posterior probability of class Ci can be calculated as the follows: P of Ci by x equals to P of x by Ci multiplied by P of Ci by P of x, that equals to P of x by Ci multiplied by P of Ci by P of x by Ck multiplied by P of Ck, where k equals to 1 to k of limit. We have the prior probability satisfying P of Ci greater than equals to 0 and the limit of P of Ci where I equals to 1 to k is equals to 1. And for the minimum error, the Bayes classifier chooses the class with the highest posterior probability. That is, we can see or we can choose Ci if P of Ci by x equals to max of k multiplied P of Ck by x. Losses and risk. Let us define the action alpha I as the decision to assign the input to the class Ci as lambda ik as the loss incurred for taking action alpha I when the input actually belongs to Ck. Then the expected risk for taking action alpha I is r of alpha I by x equals to the limit of k equals to 1 to k alpha ik multiplied by p of ck by x. And we choose the action with the minimum risk by alpha 1 if r of alpha 1 by x equals to min k of r of alpha k by x. Losses and risk 0 or 1. Loss. Let us define k actions alpha I where I equals to 1 to k, where this alpha I is the action of assigning x to Ci as discussed. In the special case of 0 or 1 case where this lambda ikd is equals to 0 if I equals to k, or else it's 1 if I does not equals to k. All the correct decisions have no loss and all errors are equally costly. The risk of taking action alpha I is given as follows. R of alpha I by x is equals to limit of k equals 1 to k lambda ikd of p of ck by x, that is equals to k not equals to I of p of ck by x, that is equals to 1 minus p of ci by x. For minimum risk, you choose the most probable class.